This is section 1.1.4. How can I represent intersections? So we're going to begin this section talking about solving a quadratic equation. So that quadratic equation with the x squared, y equals ax squared plus bx plus c. So the methods we have to solve: square roots, factoring and using the zero product property, quadratic formula, and completing the square. Completing the square we'll be talking about later in the year. And we'll be focusing in this section about those first three methods: square roots, factoring, zero product, and quadratic formula. So for problem number 1, x squared equals 4. What we could do is we can solve by square roots. We're going to take the square root of both sides. We get x equals. Now when solving by square roots, we get two solutions, because the square root of 49 could be a positive 7 or a negative 7. So we put plus or minus 7. There's our two solutions. Problem number 2, we can use square roots as well. We just have to isolate that x squared. So we're going to add 125 to both sides. 5x squared equals 125. Divide both sides by 5. X squared equals 25. And now take the square root of both sides. So x equals, solving by square roots, two solutions, plus or minus 5. Number 3, we can factor these quadratics. Because of the x term, that positive 4x, we can't solve by square roots. So what we're going to do is we're going to factor. So remember, you want to use x for the front of each term. Think about the numbers that are going to multiply to negative 21 and add to 4. That's going to be a positive 7 and a negative 3 equals 0. Now here's where we use that zero product property. Set each factor equal to 0. X plus 7 equals 0. X minus 3 equals 0. So subtract 7 from both sides, you get x equals negative 7. Add 3 to both sides, x equals 3. There's our two solutions: negative 7 and positive 3. For number 4, we can factor as well. For the first spot in each factor is an x. Think about the numbers that multiply to positive 48 and add to positive 14. So it would be a positive 8 and a positive 6. Set x plus 8 equal to 0. Here's that zero product property. X plus 6 equals 0. So x equals negative 8 and x equals negative 6. Those are our two solutions. Numbers 5 and 6 are the more complicated factoring problems. So we talked about these during our factoring review. At the top, multiply the first and last terms, you get a negative 4x squared. The middle term is 3x. So think about what's going to multiply to a negative 4x and add to 3x. So to multiply to negative 4 and add to 3, going to multiply to negative 4 and add to 3 would be a negative 4 and a positive 4 and a negative 1. So we could put 4x here and a negative 1x here. So now we draw our box. From the original quadratic, our 2x squared can go up here, our negative 2, and then the 4x and the negative x go in either one of these in the diagonal. You can put 4x here, it doesn't matter. Negative 1x here, negative x. So the common factor of these two terms in this row would be x. The common factor here is a positive 2. Common between these is a 2x, and common here is a negative 1. So there's our factors. Our factors are 2x minus 1 and x plus 2. So now set each factor equal to 0. 2x minus 1 equals 0. X plus 2 equals 0. So you get 2x equals 1. Divide both sides by 2, x equals 1/2, and then x equals negative 2. Those are our two solutions, factoring and using the zero product property. Number 6, once again, we'll draw our diamond. Multiply the first and last terms, we get 90x squared and a 21x on the bottom, that middle term. So think about the numbers that multiply to 90 and add to 21. So now to get a 90 and 21, we want to think about combinations that might work. So thinking about different combinations that multiply to 90 and add to 21. So the multiples of 90, so we have like 9 and 10, that won't add to 21. We've got a 30 and 3, that doesn't add to 21. Let's try 15 and 6, and that will add to 21. So we have a 15x and a 6x. Draw your box now. Remember, in the box, the 9x squared from the original and the 10 from the original. And then we fill in those in the other open spots. 15x here, 6x here. It doesn't matter if we flip those around. So look for the common factor. We have a 3x, we have a 5, we have a 3x, and then we have a 2. So the factors are 3x plus 5, 3x plus 2 equals 0. So now the zero product property set each factor equal to 0. And 3x plus 2 equals 0. So 3x equals negative 5. Divide both sides by 3. X equals negative 5 thirds. 3x equals negative 2. Divide both sides by 3. X equals negative 2 thirds. So there are our two solutions. Going to the next page. Looking at these quadratics, they're not factorable. And remember, if we're not sure if they're factorable, b squared minus 4ac. So it would be negative 12 squared minus 4 times 1 times 4. So it's going to be 144 minus 16, and that is 128. That is not a perfect square. This is not factorable. The only way to solve a quadratic without factoring is quadratic formula. X equals the opposite of b plus or minus the square root of b squared minus 4ac, all divided by 2a. So the opposite of b, the opposite of negative 12 is 12 plus or minus the square root, negative 12 squared minus 4 times 1 times 4. All divided by 2 times a, which is 1. So we get x equals 12 plus or minus. Now I already found b squared minus 4ac, so I can just put the square root of 128 all divided by 2. Now that this is Algebra 2, we have to talk about simplifying these radicals. So the square root of 128, the largest perfect square factor of 128 is 64. So it's the square root of 64 times the square root of 2. So that simplifies to become 8 square root of 2. So x equals 12 plus or minus 8 square root of 2, all divided by 2. Once again, Algebra 2, we want to go a little bit further with this than we have in the past. So x equals, I'm going to split them up. I'm going to give them both a denominator of 2. 12 over 2 plus or minus 8 square root of 2 divided by 2. And now I can finish up. 12 divided by 2 is 6 plus or minus 8 divided by 2 is 4, and then the square root of 2. And there is our solutions. Let's check to see if this is factorable. B squared minus 4ac, negative 5 squared minus 4 times 5 times negative 2. So I get 25 plus 4 times 5 is 20, times 2 is 40, plus 40, that gives us 65. Not a perfect square, not factorable. We have to use the quadratic formula. x equals the opposite of b plus or minus the square root, b squared minus 4ac, all divided by 2a. So the opposite of negative 5 is 5, plus or minus the square root. Negative 5 squared minus 4 times 5 times negative 2, all divided by 2 times 5. So x equals 5 plus or minus. Now we already found b squared minus 4ac, so it's the square root of 65, all divided by 10. Now the square root of 65 cannot be simplified, but what we can still do is x equals, and we'll split them up. 5 over 10 plus or minus the square root of 65 over 10. And the one bit of simplification we can do here is that 5 over 10 is the same as 1/2. So it's 1/2 plus or minus the square root of 65 divided by 10. And there is our solutions. Problem number 9. It says find as many ways to find the point of intersection of the two functions. What we're doing is we're finding out when these are going to be equal. Now, we're going to solve it algebraically, and then I can show you the graph and the table to help us solve as well. So we want to find out when they're going to be equal. So really what we're looking for is when f of x equals g of x. We're going to set the two equations equal because everything's going to be the same. So what we get is 2x squared minus 5x plus 6 equals negative 2x squared minus x plus 30. Now we want to get everything onto one side of the equation. So I'm going to add 2x squared to both sides. I'm going to add x to both sides. And I'm going to subtract 30 from both sides. So I get 4x squared minus 4x minus 24 equals 0. Now looking at this quadratic, I can see that they're all divisible by 4, all those terms. So I'm going to factor out the 4. 4 times x squared minus x minus x minus 6 equals 0. Now what I can do is I can divide both sides by 4. So I get x squared minus x minus 6 equals 0. And now what I can do is I can factor this quadratic. X and x. And now think about what numbers multiply to negative 6 and add to negative 1. Well, that would be a negative 3 and a positive 2. So x minus 3 equals 0. So you get x equals 3. X plus 2 equals 0. So x equals negative 2. So now that's just our values for x, but an intersection has an x and a y component. So what we need to do is we need to find out what value of y would we get. And to do that, we can either go into f of x or g of x. They both are going to work. So y equals, I'm going to use the f of x just because I don't feel like dealing with a negative. 2 times 3 squared minus 5 times 3 plus 6. Order of operations, 3 squared first, so it's 2 times 9. Minus 15 plus 6. So we add them up, 18 minus 15 plus 6. We're going to get y equals. 18 minus 15 is 3, plus 6 is 9. So one of our points of intersection is at 3, 9. And now we're going to have to use the negative 2 to find the other one. So it's 2. And now negative 2 for x now. Negative 2 squared minus 5 times negative 2 plus 6. So y equals negative 2 squared is 4 times 2 is 8 plus 10 plus 6. So y equals 18 plus 6, which is 24. So our other point of intersection is negative 2, 24. That's our solution. Now, here's how we can find it on Desmos. So what we're going to do is we're going to type in both equations. y equals 2x squared minus 5x plus 6. Then we're going to go down to the second one by just using you can just press your screen. And then you get y equals negative 2x squared minus x plus 30. And we need to kind of zoom out our screen a little bit. And when we do that, we can actually see where these two graphs intersect. So we can see the point of intersection. There's one at 3, 9. And the other point of intersection is right there at negative 2, 24. You can see it's on both equations at the same time. That's using Desmos. On the graphing calculator, y equals, so you get 2x squared minus 5x plus 6. That's in y1. Hit enter to get the y2. Negative, make sure you use the negative symbol, negative 2x squared minus x plus 30. When you graph it, you're not going to see much because the graph is a little bit too big for our viewing window. But here's where the table is useful to find the solution. So let's go to the table, second table. And you can see, look for when they're equal. They're equal right here at negative 224 and at 3, 9. You see how the x has the same values for y. So that's using multiple ways to solve the same equation. Let's go to those last few problems on the next page, please. Now we want to sketch a graph that has x-intercepts at negative 5, 0, 2, 0, and 6, 0. So we're just kind of adding on to what we had done earlier in a previous section. So now those are our intercepts. That's where the graph is going to cross the x-axis. Our domain, so we're going to be between negative 5 and 7. So I'm going to draw my lines here, my vertical lines at negative 5 and 7, and a range between negative 4 and 10. So I'm going to go all the way up here to 10. And negative 4. So we want to make sure we stay inside of that box when we draw our graph. And since it has or equal to's, we have to make sure we touch the outside of that box. So what I could do is there's multiple correct answers. I'm going to go right away, just go all the way up, back down through this, all the way down, and then back up. And then I can have it stop here, and I'll put a closed dot at either of those points. That's not the only correct answers. That's one of the correct answers. And the last one, our x-intercepts are at negative 4, 0, positive 2, 0. Now the domain is all real numbers, so we're going all the way left, all the way right. And for y, it's greater than or equal to negative 8. So here's my line. We want to make sure we touch that line, but we never go past it. So a quick way to do that would be a parabola. I don't want to give myself more than those intercepts given, so I was kind of stuck using a graph similar to that. But remember, another graph it might look like, it could look something like this, like a W almost, where it's kind of doing the same, but you can see down here it's never crossing that x-intercept again, or the x-axis. That's it for section 1.1.4. Thank you.